Hello, let's see a demonstration on how to exploit a buffer overflow on a Linux x64 system to obtain a shell. So we have a simple code of bof.c. Let's see what that code is. So there is a main program. It has this command line arguments, so number of arguments, and then the arguments itself. So we've declared a buffer of size 200 here, and then we're calling strcpy function to copy the argument read from the command line into the buffer, and then we're just plainly printing the buffer. So this is our code here, and we're trying to exploit the vulnerability of strcpy. Let's see how we're doing that. So before that, let's assume that we all have a basic understanding of register set and usage, and the way the stack grows, and also where the return address is, and also how to use GDB, because we'll be using peda GDB over this tutorial. So what is a buffer overflow? If we see that character buffer of 200, that means in the stack we have a fixed memory for this buffer, that is a fixed size 200, and then when we're calling strcpy, what happens is, to this buffer where it's fixed in the stack, where we have given already a memory space in the stack, this argument is copied to that buffer. So if you could just see an image of how it looks like, here is our buffer in the stack, and then we have some space over here, and this is the return address of our main. Right, so this is the specified space given for the buffer, and suppose we read an input that exceeds the size of this buffer, then what happens? It goes over here and it overrides some things that it should not be actually overriding. So it goes up till here, and then as the string grows, it can even override the return address. So our catch here is to override the return address and make it point to an address of our choice. In this specific case, make it point to an address of this code where our attack code is placed, of the shell code. So that is what buffer overflow is, and let's see how to do that. In most of the modern operating systems, it's not very easy to exploit this because there are lots of stack protections enabled. So before starting with our tutorial, we need to disable them. So the stack protection, some of them are ASLR. ASLR is address space randomization. Then we have stack canary, and then NX. So we can disable ASLR by typing away this command on the terminal. Before that, make sure that you check the value of this file. For me it was 2, and after completing the tutorial you can enable it by giving the default value back to this command. So instead of 0, write 2 here, so you'll get it enabled again, and then use these flags to disable these protections. Right, so let's go ahead and compile our bof.c. So let me copy paste this. I've already disabled ASLR, so let me disable the other protections as well. Okay. I have copied the new line too. Okay, let's see, GCC. That should do. Yes, so let's go to GDB. Okay, so in order to check if you have disabled all the protections all right, let's type this command in GDB, checksec. Yes, we see that these protections are disabled. Let's now not go to this particular protections, because we will not be using that, we'll not need that in our particular attack over here. So yes, now that we have disabled it, what is our main aim? Our main aim is to override the return, the RIP, the instruction pointer, with address of our attack code. So in this case, our shell code. So I've got a shell code from this site called Shellstorm. That's a 27 bytes long code. You can write your customized shell code too. So this just opens a dash shell. Right. So let's just go ahead and run our program first. Let's see how it's running. So let's give some inputs. For that, let me write a simple Python script to, let's give, so the buffer is of size 200. Let's give some A's. So A of size maybe 210. Let's try to exceed the buffer. Yeah. Okay, so in fact the stack is, it's not just 200, it has given some extra space too, so it's, we have not yet received a segmentation fault, but still something might have happened, so we don't know. Let's try say 250. Again it's normal. Let's say 220. Okay, so now we've received a segmentation fault, and if you can just notice the return address, the return address from the main, we can see that some 4141. So this is a hexa for A. This is nothing but the A character that we have given, and we have partially overwritten the return address. So let's try and manipulate to get full control over how to override the return address. So let's see, 216. Okay, now let's just say B. So B will be 42 in hexa. Let's say 6. Okay, so if we see that we have 6 B's over here, and if you can, we have some doubt, let's try giving 5. So there's only 5 B's. Right, so we have got full control over the return address. Now we can write whatever we want over here to manipulate our attack. That's good. So yeah, one important thing to note is that on x64, addresses greater than 48 bits will raise an exception. So you should not give whatever address it is into 8, because that will not be a valid address in any case. So try to give it 6, because if the maximum address possible is from 0000, then all F, right? So yeah, that's just a point to note. And okay, now let's do something. Okay, let's see how we are going to go ahead with the shell code attack. Let's see this image. So this is our stack here. So right now we have a return address here. We have overwritten this with a few B's, right? And then until that we have put some A's over here. We have consecutive A's over here. So instead of the A's, let's put NOP. That's a NOP instruction. That's an X90. So what NOP does is it just goes forward to the next instruction, right? So what we are going to do now is we are going to put some NOPs, and then we'll put the shell code, and in the return address space we'll put an address of somewhere around here, so that when it returns, it goes back here, and then it goes to the next instruction, and then bang, we'll reach the shell code. Let's try and do that. So instead of A into 216, let's put X90 for the NOP instruction. Good. So we have got some instructions. So let's examine what is over there. Let's see. So this is the address space, and if we go and see, we can see a lot of X90s over here. So this is the space where we have just overwritten. So let's try giving this address, right? Let's make the return address point to this address. Okay. let's do that. Okay, so this is little Indian, so we'll have to give it in the reverse order. Instead of 6Bs, let's give the address. So that is XA0, XE1, XFF, 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 X7F. Right. Okay. So that is the return address. Now let's put our shell code in between. So I've already copied the shell code from the website shellstorm.org. That's 27 bytes long, in fact. So let's just copy it. So right, so now we've got 216 nopes, then 27 bytes of shell code, and then the return address. But there's a mistake here, because now this will overwrite the return address, right? Because 216 is the offset, and just after 216 you're overwriting into the return address. So we need to make sure that this entire set is just 216. So how many NOPs should be there? We should reduce the number of nopes, so that is 216 minus 27. Let's see what that is. So that's 189. So let's go ahead and see if we can get it working. So right now we have inserted 189 nopes, then we have a 27 bytes of shell code, and then in the new address we have put the address of somewhere here. So if everything goes right, let's see if we can get a shell. Okay, and yes, we have got a shell. So we can just check it by typing a command, say who am I, or say who in that, so we can see the result. So now we have successfully exploited a stack buffer overflow. Thank you for watching.